Right, let's go ahead and get started. So just as a bit of a recap, what we did last time, we sort of wrote this core math file that just has a bunch of pretty simple functions, some more complex ones with a bit of weird C++ syntax. We aren't going to be using these like immediately. These are more for when we actually get towards the near the end of this project, actually, when we're making games. Like all this math stuff is useful for programming game logic, but you don't really need it when you're setting up the rest of the behind the scenes stuff. So it was mostly just like a warm up, getting you into C++, and hopefully it was effective in that. There were a few people who said I was typing too fast, so I'll try and keep that slower this time, and I'll also try to explain like when I'm copying stuff, because I realized that last time like I copy pasted a bunch of stuff and I probably didn't tell you why or what I was doing, and it may just look a little weird if it sort of pops up on the screen and I'm scrolling around and stuff. So in general, I'm just going to try and make it a bit easier for you to follow. I'm also going to zoom in here. But yeah, one thing that I realized I said incorrectly, which you may have not noticed, it was a very small thing, but I said that atan2, this method, this sort of standard method here, gives a value between negative 90 degrees and 90 degrees. That's not true. It actually gives a value between negative 100 degrees or 180 degrees and positive 180 degrees. So it gives you the full circle. And it's able to do that because you give it actually a vector, whereas for the just regular standard atan function, you have to give it a value, like a computed ratio of y over x, and so it can only resolve that to half a circle. So in general, I think atan2 is a bit more useful. But again, we won't use that for a while. So was everyone able to download the stuff from the GitHub successfully? Did that work for everyone? I'm going to assume yes.
Yeah, it worked for me.
Okay, cool. So as I said, someone asked about it, and I said like it's not necessary this time, but in future I will probably end up making like bigger changes, just because as I'm writing this during the workshops, like I'm going to be taking shortcuts and like putting things in weird, ugly places just to avoid scrolling around and all of that. But then eventually I will sort of fix all those small little details, and I think it's good for you to have that just because the next time that the class starts, you'll have the same version of the code as me, and everything will be in the same place, and so it'll be easier for you to keep up. Okay, so with that said, we're now done with this core file. We're going to move on to our two structures for the math library, which I think we'll definitely get done today. And if we have time at the end, I've prepared like a presentation about GPUs, graphics programming in general, OpenGL. So we can go through that just to sort of get everyone, up to speed on that whole paradigm, I guess, because it is pretty detailed. Okay, so this class is going to be called Vec2. I called it Vec by mistake. You could just rename that by highlighting it in this Solution Explorer over here. And then in our all.h, I'm going to copy this, and we'll go ahead and include that there, just so that we can test some of it in our main file here. So all this is going to be is a 2D vector class. Very simple. It's sort of like a classical example, I think, in C++, just because it's very simple, but also you can do some cool like C++ specific stuff with it, like making it a template class so that it expects, or it contains values of an arbitrary type. The one we're going to be focusing on, though, is operator overloading, which is one of my favorite features of C++. I think it's very cool, and you don't see it in any other language that I know of. I'm not sure. C Sharp may have some of it because it's sort of a derivative of C++, but certainly not in Java or JavaScript, anything like that. So the first thing I'm going to do is make everything public. This is mostly for convenience, but also sort of to follow convention. So we're going to have our two values here. I'll just call them x and y, because this is a vector. So basically that's what it represents. And t, remember, is just like this generic type, which when we create a vec2 could be an int, it could be a float, it could be whatever. And the reason I'm leaving these public instead of doing the typical, like t, like get x, return x, like you would see in Java, and then you have a setter as well. That's just a lot of typing, it's unnecessary, but also with like simple mathematical structures like this, and especially ones that use operator overloading to like make them more similar to the primitive types, it's very common to leave the data fields public just for ease of access, and I'll sort of explain what that means when we start using this. So let's just write our constructors here. I'm sort of assuming that you've read, at least to some degree, the Const Correctness article, because we are really going to sort of hit that hard here. This should be familiar syntax to you, just a const reference to a t. Again, in most cases this won't matter because these will more than likely be just floats or ints or whatever. But if in some case it's like a more complex structure, we want to avoid copying that, so we'll take it in by reference. Then we have the copy constructor, where we will create a vec2 from another vec2, basically just copying its values. I'm going to go ahead and do this for now, and we might come back to this a bit later. Oh, by the way, this is just a bit of C++ syntax, this sort of colon, and then you initialize the values here. This is equivalent to doing, like in the body of the constructor, saying x equals underscore x and y equals underscore y. It's just nicer to do it here. I don't know exactly why. Again, that's sort of a convention thing. I'm sure there's some optimization that can happen with that. But also it's just sort of nice to separate out any sort of logical part of your constructor that you may have, and just the boilerplate like assigning to variable stuff. It makes it cleaner and easier to read. And then we will have another C++ specific thing here, a move constructor. And this operator equals thing we're about to write. But a move constructor takes in a special type of reference called an L value reference, which is denoted with this double ampersand here. I realize now that L values and R values are kind of a niche thing. I did recommend that you study those in like how you should prepare for this. I made like a list of things you should look up about C++, but I'm not sure how many people actually did that. So I don't know. I'm just going to leave that for now, and if we run into it a bit later, I'll explain more. Maybe at the end, because I think we'll have some time at the end today. Okay, so now we're going to overload the equality operator. We're going to have it return a Boolean, just like it usually does. So all this is going to do is it's going to say, it'll allow you to compare two vectors using the double equals operator. So if I have a math vec2 of floats here called A, I'll use my constructor that has 1 and 2 as its values, and then one called B, which has also 1 and 2 as its values. And then we want to check if they're equal. We can do A equal B. And you can see now if I build this, compile it, okay, well it's saying it must return a value because obviously we haven't finished this, but this part is not yelling at me. And that's really cool, because if we didn't have this at all, it'll say binary equal, it does not define this operator, blah, 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 blah. So instead of now having to do like A, dot equals B like you would in Java, it's just really ugly. You can make your code easier to read by just writing the double equals operator. Okay, so let's go ahead and write this. I'm going to make use of our the is0 function we did last time that like has this sort of standard error that it checks. If we go back to is0 here, it just checks if the absolute value of whatever argument it takes is less than or equal to some very small number. So I'm going to go ahead and use that because, as I sort of explained last time, like it's good for comparing velocities and stuff when you don't need them to be perfectly accurate. Okay, so now that we have this defined, if there's a very small difference between x values and a very small difference between y values, I'll say these two vectors are equal. So let's go ahead and run this real quick, and we should just get 1, because 1 equals 1 and 2 equals 2. There we go. And just for the sake of proving it, if we change b to 1 and 2.5, we should get 0, because the y values are no longer equal. Okay, now we'll do a similar overload for not equals. Of course, taking in the other value by reference. Now we could just do return not.
I'm sorry, I'm having trouble following. I think you're you're still going a bit too fast.
Okay.
Yeah.
Sorry. Which part did you get to?
I'm still like testing the code for the operator overload.
Okay. I should have said like you guys don't need to do that, right? Because like whatever you write should be, or yeah, like you're writing the same code I am, so the test results I get should be the test results you get. So I'll try and mention that when I'm just doing something like for the sake of example, and I don't expect you guys to follow, because that was a lot of jumping back and forth. I see how that could be confusing. But yeah, okay, so we have this double equals operator, and now we want just one for not equals. So we can do this, A not equal B. And we could do like not operator equal equal other. That would be fine. But for the sake of being like technically correct, we can use the feature of short circuiting inherent in the logical operators to make this potentially a little bit faster. Because now if the x's aren't equal, it won't even check if the y's are equal. So yeah, we'll just do it like this. If either the x values aren't equal or the y values aren't equal, then the whole vector is not equal. And I'm not going to test that because that's pretty much the same as the first one. Okay, now we're going to define this operator equals up here that we used in our move constructor. This is going to return a vec2 reference, which I'll explain in a bit. And it's going to take in a const reference, of course. And we're just going to set x equal to other.x, y equal to other.y, and then return this dereferenced. So you're probably somewhat familiar with this if you use Java especially, or JavaScript more especially. But this is basically just a pointer to the current object, right? So like if I was calling operator equals on my vector A up here, then this would be a pointer to A, essentially. And so when we dereference it, we get a value. So this is a vec2 pointer. We dereference it to get a vec2, but then we take care to return it as a vec2 reference, because again, we don't want to copy anything. There's no need to copy. So all this is some, just like, again, like making it very easy to do stuff. So if I go back to this example, and you don't have to write this, I'm just proving this works. So if I go back to this example, it should print 0. Yes, because A is 1, 2, and B is 1 and 2.5. Those are not equal. But if in between here I do A equals B, which I can now do thanks to this equals operator, there we go. It works. And it copies the value of 2.5 into the value, into the Y place of A, if that makes sense. And then we're just going to use this operator as we did up here in our move constructor, and we can also, if you want, go ahead and use it in your copy constructor. Just like that, same way, just to avoid rewriting code. Okay, now we're going to do some of the math stuff. This is going to be a good deal of copy and pasting, so I'll try to make it very clear what I'm doing. So this first one, we're just going to add a constant value to both of our fields. And we are doing this by returning a new vector. So we're creating a new vector here and returning it. So if I were to do, and that makes sense, right? Because if you do something like this expression, a plus 5, what you don't want it to do is change the underlying data of a, because that's not how that expression reads. What this expression reads is, okay, I have my values in a, add 5 to them, and give me a new thing that stores that result. So how we could make use of this is by specifying a new vec2 c that is equal to a plus 5, and that would hold the values of 6 and 7. Okay, now I'm going to copy this and modify it just a bit. We're still going to return a new vector, but we're going to take in a vector as well as our argument. And I like to name the single values t and the vectors other. It just helps prevent me from getting confused. And we'll just do element-wise addition on this. So x plus other.x and y plus other.y. Okay, so now, in addition to this, we could have a new vec2 called d, which is equal to a plus b. And that would have 1 plus 1 is 2, and 2 plus 2.5 is 4.5. So I'm just going to sort of show you this really quickly. You don't need to copy this. I'll print out our two new vectors here, c and d. Once again, c should be 6, 7, and d should be 2, 4.5. Oh, I messed up. I forgot to remove that colon. So if you don't do this like, I can't remember what this is called, but if you don't do this syntax where you like initialize stuff before the constructor runs, you don't put the colon. I just forgot to delete that there. Now we should be good. There we go. So we have 6 and 7 in C, which is correct, and 2 and 4.5 in D, which is also correct. Okay. Now, I guess for those of you who haven't read the const correctness thing, I should cover why I'm putting this const right here. Does anyone know what that means? This const at the end of the method, like header or signature.
I think it means like you don't want the contents of the method to change after you've run it, I guess?
Close. It's sort of the other way around. So what this says is whatever object this method is running on, don't change the contents of that object. And this makes sense in this case, right? Because we're returning new vectors from both of these functions. So x and y remain constant. And what this allows us to do is sort of propagate const correctness throughout our program by allowing us to perform these operations on constant vector objects. So if I were to mark A and B as const vectors here. And I could to C and D as well, but that doesn't matter in this case. Because I'm using just these plus operators, which are marked as const, this will compile and run exactly the same. You can see like this. But if now I went and did that A equals B thing that we had earlier, this is what you love to see. The compiler is yelling at me. It says no operator equal matches these operands. Const vec2 equals const vec2. So the B part is correct because the operator equals function here takes in a const reference and B is a const vector, so that checks out. But the left-hand side of this argument, A, is also a const vector, and this function is not marked as const, meaning that constant objects of this type cannot invoke this method. Now you might say, okay, well just mark it as const, and then you can see it works totally fine over here. But if we are to compile this, the compiler will yell at us in a different place over here. It says, hey, you said this is const, but then you are changing these variables, so clearly it's not const. So it just won't even compile it, which is excellent. So that's what that sort of trailing const there at the end does. I know that can be a bit confusing. And geez, when we get into like passing around pointers and stuff, like the number of consts in our method headers is just gonna go insane. So it's good to sort of get a solid foundation for this stuff while it's simple. And we'll talk about eventually that whole like marking methods as const and not being able to change the contents of the object within that method. There's sort of an asterisk there. There are ways around it that the compiler will allow. But that's more advanced, and we'll talk about that later. Okay, so now we're going to do, I'm just going to copy both of these methods, and I'm going to add an equals to the operator. So now we're overloading the plus equals operator, which obviously the first thing we should do is remove this const, because when you see an expression like a plus equals 5, you expect that to change the value of a. And so instead of returning new vectors here, we are just going to do x plus equal t, y plus equal t, and then in this case, just like our operator equals method, we're going to return a reference with the same syntax, dereferencing this. And the reason for this is so that we can chain stuff together. So like, if this was just void, which you might be tempted to do, because you know technically this has the same functionality. It adds stuff to both operands. Oh, I need to remove the const from that. So if you mark that as void, then you couldn't do b plus equals a plus equals 5, because the value of this expression here, when it's resolved, is void. It's of type void, and obviously that doesn't make any sense. But if we mark it as a vec2t reference, returning this, then you can chain them, which is excellent, because this really helps them behave as sort of these primitive types. Okay, I'm going to make the same modifications to this second operator plus equals, return a reference, of course, and then again do the element-wise addition, x plus equals other dot x, y plus equals other dot y, and returning the dereference to this pointer. So is everyone good up to this point? Because we're about to do a bunch of copying.
So far, yeah.
All right. Am I going at a better speed, or is it still a little fast?
It's getting better.
Okay, cool. So now that we have these, we're going to do something really boring. Just highlight all 4 of these methods and paste them once for, so we have addition, now we're doing subtraction, one more time for multiplication, and one last time for division. So let's scroll back up here and start changing those. So we have, and I'll add comments as well, so it makes it easier to see. So we have add Next we're going to do subtract, and all we're doing here is changing the operators. Unfortunately, I don't know of a cleaner way to do this. Like, it would be very cool if there was a way to, like, in addition to generalizing types, you could like generalize operations that happen, but I don't think that's a thing, unfortunately. So we do have to copy and paste this, but it's just a one-time thing, and it ends up giving us a bunch of cool functionality. Okay, so that's subtraction. Now I'm going to do multiplication. Just replacing all of the pluses with multiplies. And finally, division. Okay, so I'll give you guys a few seconds to catch up there and just show you over here that now all of these expressions that we did using addition, we can also do with subtraction or multiplication. So we could do b times equals a, minus equal 5, and that'll be totally fine. And yeah, that's essentially our vec2 class. We have a couple more methods here, but we're done with overloading all these operators, the boring stuff. So I'm going to move on here. Now we have some more methods. Just a very simple one to get the magnitude of a vector. We will use our distance function from the core file. Just return the distance from 0, 0, or the origin, to our vector's position, which will give the length of our vector. Another useful one, or useful operation, is to normalize our vector, which maintains the proportions of it. That is, like, the angle of it is the same, but it's of length 1. And this can be useful when you only really care about the direction of the vector, but not the magnitude. So whether or not your vector has magnitude of 100 or 0.5 or whatever, if you normalize it, it'll keep the same exact direction but have magnitude 1. And that can simplify some calculations. And this is we're going to use our operator operator divide on the magnitude, because all this does, remember, is perform element-wise division. Well, that's not a good way to say it, but it divides both of our x and y values by t, which in this case is magnitude. And that will maintain the proportions, but make it length 1. We'll have a similar method here that returns a reference called normalize, and that is not going to be const. And this is actually going to alter our vector. And so here we're going to return operator divide equals magnitude, which, if you look up here, actually modifies our values and then returns itself. So this is where, if you don't want to change the host vector, you just need a normalized version of it. And this is where you really don't care what happens to the host vector. Like, you only need it for direction. That's the only calculation you're doing with it, so might as well just normalize the existing one. Okay, now we're going to do dot product, a very classic operation. Return this x times other dot x plus this y times other dot y. Not much to say about this one. Now we have angle, so we can get the angle of this vector. I should say between this vector and the horizontal axis, the x-axis. We will use our atan function for that. X comes first, y comes second. And now we have sort of a cool one that I'll do a bit of a demonstration for in Paint. which is the angle between two vectors. So I'll write out this crazy formula, and then I'll explain it. Okay, so it's not actually that crazy, but it does look a little weird. Like, sure, there's an acos here, so it's something to do with angles, but how does whatever this is resolve to like the angle between two vectors? So let me bring up Paint here. And I'll draw a small coordinate system. Let's say we have, we have vector A, which is this red one, and vector B, which is this one. So obviously vector B has an angle, I'll call that theta B, and then vector A has an angle theta A. So the angle between these two vectors, when you can see it graphically like this, I'll just call that theta, is very clearly theta A minus theta B. But we can perform some optimizations on this, because if you look back at our code real quick, how do we get theta? Well, we have to use this angle method, which uses arctangent. And arctangent it's an expensive operation. Like, it's gotten better. This optimization would have been much more important back in like the 90s, but now I'm pretty sure that modern CPUs, I think they have like straight up just instructions for all of this basic trigonometry stuff, as well as square root. So that was something like I remember Eduardo pointed out last week, that or on Saturday, that fast inverse square root algorithm, which is very cool, but nowadays it's completely useless because our CPUs just have a square root instruction, and so it's way faster than anything you can write in C, even with all the magic. But still, in this case, it's much faster to do like a single trigonometry function, arc cosine here, with some dot product, which is just multiplication and addition, and magnitude, which is, square root, again, a very simple CPU instruction. And so that's the problem here, is that this theta requires an arctan, and this theta requires an arctan. So we can improve this using the function, or sorry, the definition of dot product, and that is A dot B is equal to the length of A, or the magnitude of A, times the magnitude of B, times the cosine of the angle between them. And we can sort of simplify this out. Remember, we're trying to solve for the angle here. So we divide by magnitude of A, divide by magnitude of B, we get the cosine of the angle. And then obviously, if we want to get the angle, we just have to take the arc cosine of everything on the left side, which is A dot B over magnitude of A times magnitude of B equals theta. So that very simple sort of algebra manipulation has allowed us to reduce what was previously one atan minus another atan, both pretty expensive, to a single expensive instruction and some other stuff, some addition and some multiplication, which is much better. So that's why we do that. Okay, so is everyone good on the vec2 class? Because that's it. All right, moving on, I'm going to create another file here. This is our second and final class for the math library, called range. This one is not as widely used. I'm sort of using it to introduce you to a couple more concepts that we'll see later on, but also we will probably end up using it. It's very good for like error checking, and we'll see why in a minute. Before I do anything though, I'm going to go ahead and include this in our all.h, just so that we can do some testing with it over in main. So I'm going to go ahead and delete all of that. vec2 stuff. Okay, put this in our namespace math. It's going to be, I always spell this wrong, type name. There we go. It's going to be similarly templated, but most often used with floats, ints, just like the vec class. In this case, though, because it's not quite like, I guess it is like a mathematical structure, but not in the same way as a vector. Like you're not going to be doing many operations on range. It more exists to store a range and then check things against that range, or maybe clamp values into that range. So there's not really a need to make its variables public access. And also, I think it's a lot smarter to have something like this be just totally immutable. Again, because there aren't many operations that you need to do on it in the first place to mutate it. So I'm going to store these as private variables. And this is sort of my syntax. I tend to, when stuff is public, as you saw in the vec2 class, I'll just call it what it is, because you're going to be the user is going to be accessing it by name. So in this case, X and Y is very clean. But when it's private, I like to have this sort of im underscore, which signifies that this is a member variable. And it does seem kind of annoying to have to add this to everything, but trust me, it really does help if you have some complex like functions to denote what is a property of the object being operated on and what is some external value. And I found that has helped me make fewer mistakes. So our constructor here, basically the same as the vector. We're just going to take in two values and set this object's values equal to those with this little initialization list up here following the colon. But then in the constructor, we're going to do a simple check to say if min is greater than max, we're just going to print an error and say like range min must be less than max. But really what you could do some fancy stuff here. You could like have an assert or something, or like in Windows there's this debug break thing, I think, if you include windows.h, but that's platform dependent, so I don't want to deal with that. This is good enough for us. Just letting ourselves know that we've messed up. Because obviously a range where the minimum value is greater than the maximum is completely useless and doesn't make any sense, so we don't want that. Then again, just like our vector, we're going to have a copy constructor, which makes use of the equal operator that we will define in a minute. And just under that, we will have the move constructor, which will use that same operator equal. And after this, I realize this is confusing. Like I haven't really talked about the lval versus lval versus rval stuff. I'll do that after we finish this. This is a much shorter class than the vector. Okay, we're going to define the operator equals, which is const, of course, because it does not change any values. And we're going to use the exact same formula as for our vector. Then we'll do the not equal, which if either the minimums are not equal or the maximums are not equal, then the whole thing is not equal. Okay, there are those. We're going to do one more operator overload, and we can come back to this later if we need, just because it's trivial to implement. I mean, the vector stuff was as well, but that was more for the point of showing you the different ways of doing operator overloading. But now that you've seen that, we don't really need to. So as I said before, I like to make my range classes or my range objects immutable. There's just not really a reason they should change. So when we want to add some constant value, we want to offset this range by some value, we'll just return a new range by adding that value to our min and our max. There we go. And this syntax may also be confusing. Technically, this could also be written in a more Java-like way as range, like using the constructor. But C++ has some weird stuff where you can sort of interchange the proper constructors that you've defined with these sort of brace initialization lists. And really, I think these brace initializers should be used more for structs instead of classes, just because structs are generally, they come from C. They're generally thought of as just a simple grouping of data and nothing more. Everything is public. It's just a bunch of stuff thrown into one place. Whereas with objects, I think it's just nice to separate them out. So I'm actually going to write it like this. We'll return a range T. Even though, once again, these two expressions are equivalent, the compiler will return the exact same thing because it knows what to do with this. But for our purposes, reading this, I think this is a bit nicer. And you could, if you want, go back into the vec2 and make the same changes. But this is essentially a struct. Like, I've made it a class. There's not really a reason, though, because everything is public anyways. And if you know, in C++, the only difference between a class and a struct is that in struct, everything is public by default, but in a class, everything is private by default. They are exactly the same otherwise. So really, I could make this a struct, and it would be totally fine. But you can or can't do that. It literally does not matter. Okay, so now we have the useful part of our range. We're going to take in a value by const reference, of course, and say whether or not our range contains this value. So if our minimum is less than or equal to the value, and our maximum is greater than or equal to our value, we'll say that our range contains this. But there's sort of a problem here, which is, what if, there are a lot of combinations you could have of this. You don't have to write this, I'm just showing, for example. So like we could have, there are exactly 4 combinations, actually. These are the 4. Inclusive on the left for 2 of them, inclusive on the right for 2 of them, and then one of them is just completely exclusive on both sides. And we could define 4 separate methods. I think that would get really messy, though. And so the way I prefer to do this is by creating another sort of struct up here, just above our range class. I'll call it range contains params. And this is only going to be used as an additional argument to our contains method to specify which of the sides should be inclusive. So all we're going to do is have 2 booleans in here, one for left side and one for right side. I'm going to default initialize these to false, and I'll show you why in a minute. This is not necessary. It's merely a convenience thing for the writer. But once we have that, we can include this by const reference, of course. I'll call it params. And you can do a cool thing in C++ if you're coming from Java. I don't think this exists in Java. You can give variables default values, provided that they're after all variables with non-default values. And so you do that by doing equals and the default value. So if I wanted my, if I was taking in some int here as well, and I wanted that to default to 10, you could do it like that. But you can do it for objects as well, and obviously structs. And when you initialize a struct like this with just sort of the empty braces list, it doesn't put any particular values in there. It'll just use what you've specified as the default values. So in this case, what this means theoretically is that the left side is not inclusive because it's false, and the right side is also not inclusive because that's false. But the user can change those one by one. So I'm sort of going to mangle this expression here a bit into like a bunch of ternary operators. You could do it with if statements, but I really hate taking up space with if statements when you can do them in a conditional. So if our params.left is true, meaning we want it to be inclusive, then we'll check it with the less than or equal to. Otherwise, we'll just do less than. And same thing for our right side. We use params.right and just switch mmin with mmax. Like that. So if our left parameter is true, the left field of this struct is true. Inclusive, otherwise exclusive. If right is true, inclusive, otherwise exclusive. Very simple. Is everyone good on this? Like, do you understand that? Because there's kind of a lot going on there that's new.
Could you repeat what the contains is supposed to do again?
The contains params?
No, just the like what you're trying to.
Oh, right.
return.
Sorry. Yeah. So this, if we have a range, I should just actually like show this. There's no reason for me not to. So if we have a range, I'll do ints called r, and it goes from 0 to 5. And we want to check if some integer is inside of this range. We would use the contains method.
Oh, okay. So if, like checking if 2 exists in there.
Yes, exactly. So we could do r.contains 2, which would be true, obviously, and then r.contains 10, which would be false. And you don't have to type this. I'm just showing. Param, I misspelled that. Oops. There we go. Wait.
Are they switched?
Oh yeah, I did mmax less than or equal to. My bad. I'm just going to rewrite this right side because that was confusing. And I'll do it on a new line too so it doesn't wrap. Okay, so if params.right is true, then we check if t is less than or equal to mmax. That was a dumb mistake. Otherwise, if t is less than mmax. There we go. So now if we run this, there we go, 1, 0, just as you see. 2 is in 0 to 5, and 10 is in 0 to 5. So that's what that method does. But then this extra parameter here, which you've noticed we have not had to specify because we gave it this default value, which is nice, because it would be a pain if you just want the default functionality to have to pass an object saying you want the default functionality. That just kind of sucks. But if we do have some edge case, like this, where 5 is one of the boundaries, this is going to say false. It's going to give 0 because by default this is exclusive. But all we have to do is pass in an object or a struct using this braces initializer list. And if you've set your if you follow the setup correctly, we're using one of the newer versions of C++, which does something really cool, which is it allows you to set only certain fields of a struct in these initializer lists. And the rest of the fields will just be given the default value, which is cool. So in this case, like say our goal is just to make this return true, right, for the sake of example, then we don't care if the left side is inclusive or not, because that doesn't matter. We're checking 5, which is on the right side. So all we need to do is say .right equals true. Let me expand this a bit, like that. And then this should give us 1, 0. Oh, okay. So this is like a good example. I kind of want you to pay attention to this. So you see here I just have this blank console. All I did was press the green run button, just as I've done before. This is a bug with Visual Studio. I have no idea what's caused it. It's been happening ever since I've used Visual Studio. All you have to do is close this console. Instead of hitting this red stop button at the top, close the actual window, and then rerun, and you'll be fine. That can get really scary when you've like changed a bunch of stuff and you're running it for the first time and nothing shows up. You're like, oh no, what did I break? But yeah, all you have to do is close the window. So you can see here, because we specified right as inclusive, now 5 is contained within this range, which is great. And we didn't have to set the left value at all. Okay, so I could do the same with 10, but I think I've made the point there. So now we'll do a slight continuation of the contains method, which instead of checking just a single value, it'll check a range. So we'll say bool overlaps. A range. So we want to return true if any part of these ranges overlap. So we'll do if this range contains the minimum of the other range, or this range contains the maximum of the other range, then this is true. And I'll just do a simple paint illustration where ranges are horizontal lines. Say this is range A, and we have another range B, which is slightly bigger and offset a bit, but you can see there is overlap here, and you can tell that because the minimum of B is less than the maximum of A, and greater than the minimum of A, which is to say the minimum of B is contained within the A range. So if that's true, then obviously you have overlap. And then there is the other case, the sort of reverse case, where A is further right than B, and now you have the maximum. The maximum of B is contained within range A. So that's all we're checking for here. And we're doing OR because you only need one or the other. You could do, I guess, a contains method that takes a range and says, like, is this entire range contained within the current range? I've never needed to do that, but you could if you wanted. It would be very simple. So this is functional. It has sort of the same problem as we did here, though, where we can't specify inclusivity, which could be a problem. So I'm going to define another struct up here, up at the top, called range overlap params. And we'll have another left and right field, but they won't be booleans. They'll be range contains params. And I will just default initialize those, which, remember, sets both left and right to false. So left.left is false, left.right is false, right.left is false, and right.right is false. And then down here in our overlap method, we will take in a range overlap params by reference, of course, const reference. And all we have to do is for the minimum check, we pass params.left, which, remember, the left field of range overlap params is a range contains params. So it says everything you need to know about how to check if this value is within this range. And then for the maximum check, we'll do params.right. So this, I'm not going to explain. Like, if you don't understand it, that's fine. It's like a bit tricky to think about, but I would like you to explain this in your own comments when you go through it this week. Just because it's fairly simple, but a good thing to figure out. Okay, now we're mostly done. We're just going to...
Could you go back to the range overlap param struct in the beginning?
Sure, yeah. So it just has two default initialized contains params.
Okay, yeah, I got it.
The left is for checking minimum and the right is for checking maximum. So now we're going to do the typical object-oriented getters stuff. Get min, just return that. Note that we are both returning this by reference, so that we avoid copying just in case it is something big, but also by const reference, because if you were to just return this by reference, that means that whatever code was calling get min could alter the minimum value directly, and if we want this to be immutable, that obviously doesn't make sense. So also, though, returning by const reference allows us to mark this as const, because a const reference cannot be assigned to, and therefore calling this function, there's no potential for minimum to be altered, which is perfect. Then we'll have the same thing for get max. Then we will just do a clamp thing, which we already wrote. We already wrote a function for this, but it's good to have a shorthand here. And all this is going to do is take some value, and if t is within this range, it'll just return t. If it's less than this range, it'll return min, and if it's greater than the range, it'll return max. That's just the clamp function we wrote last time. And then another simple method here, get span, which returns the difference between mmax and mmin, or sort of the length or the size of our range, which can be useful. Okay, so is everyone good on that? This one was pretty simple. I may still be moving a bit too fast. I'm trying to type slower and like scroll slower and stuff, but don't hesitate to point it out if I'm still going too fast. All right, so that's all I had for this time. We could like check the overlaps functionality, but again, I sort of want to leave that up to you. I guess this would be a good time to like explain what I'm expecting, because I sort of said last time that like I want everyone to write comments on the code every week, the new code that we've written. I think that's very valuable. I personally, like in my own projects, sometimes it gets away from me, but every so often I'll make a real effort to go back and comment everything that does not have comments. And it really helps you both catch bugs, sometimes just explaining stuff in simple English and you're like, wait, hang on, that's not actually what's happening at all. Then you can, fix that. The main reason, of course, is if you're working on a project with multiple people, it's just like a necessary thing. It makes it so much easier to read other people's code when you can read their comments instead of their code. But the main reason in this case, like I said, is just to help you get a better understanding of this stuff. And here, we're still doing sort of boring math stuff. There's not that much new, but starting next time, we're going to do graphics. Graphics programming is insanely complicated, and we're only doing 2D stuff, and we're only scratching the surface of 2D stuff. OpenGL is a very old, honestly very messy, somewhat out-of-date API, I would say, unfortunately. But it is, to some degree, the industry standard. It's the most widely used graphics API in the world. And it is possible. Like, it's messy, it's complicated, but it is possible to understand this stuff. I have just found that commenting stuff out immensely has helped me gain a better understanding. Like this time last year, I could barely write a tech demo in OpenGL, but now I've gotten to the point where like I can abstract stuff out in my own libraries. I can do some cool stuff with shaders and add lighting effects and all this stuff. And and do it all neatly and sort of understand more or less to a fairly high degree what's actually happening. And writing comments has definitely helped me there. So that being said, though, I still think it is best if you also download my code from the GitHub repository before the start of each meeting. Last week I posted that early just because there were some people who wanted it, like they didn't have their environment set up or something. But from now on I'm going to post it like the day of each lecture. So I really want you to write your comments, if you can, if you can't, whatever. And then the day of, download my code. It could be useful if you have a little bit of time to go through and compare our two comments, because I'll also be commenting as well. And just, see what you got right or what you explained differently, stuff like that. But I really think that doing that will help sort of ground you during these, because even though I am typing slower and I'm trying to take my time explaining stuff, I'm still scrolling around. That's confusing. And just if everything is in the same place for you as it is for me, I think it'll make it a lot easier for you to follow along, and you'll just get more out of it. So that being said, I do have the graphics presentation. I might start on that, but I also wanted to quickly go over L values versus R values. Just because that's sort of a complicated topic. Okay, so an R value is a value that is essentially already stored in a variable. An L value is a value that has been computed, and so exists somewhere in memory, but the program cannot address that value by name. So I'm going to use our vectors, our vector class, as an example for this. So if I have a 1 and 2, then A is an R value. So I can say like vec2t, vec2 float, and A2 equals A, and that'll work. A plus 5 is an L value, because even though A exists in memory, the result of A plus 5 does not exist in memory. It is not a variable, I guess. And you can see here the compiler will yell at you. Initial value of reference to non-const must be an L value. So this is kind of confusing. A lot of the C++ errors are very confusing, especially if you're coming from Java, which has, like top of the line error reporting, stack traces, everything. Unfortunately, sometimes in C++, your program will just crash, and the same level of confusing can happen when you're just writing your code even. So here, let's try and parse this a bit. What does this mean? So initial value of reference to non-const. That's the first part. What does that mean? So initial value just means what you're assigning to it, right? The thing that you're setting it equal to. That's simple. Reference, okay, we've got that because we have the ampersand. Reference to non-const is a bit of a weird, a bit of strange grammar. I think this is best explained by the Const Correctness article, though. Let me bring that up real quick. So we have Const Correctness, and this section in particular has been very helpful to me. Read the pointer declarations from right to left. And you also read the const declarations from right to left. So a const x star means a pointer to an x that is const. Similarly, a const x and, as said here, means a reference to an object that is const. So x is a reference to x that is const. And we can see that exact same syntax happening in our program right here. A2 is a reference to a vec2 of floats, but it is non-const. So that's what this is saying. Reference to non-const. If I were to set this as const, this would work fine. And this is a bit of a weird thing that I'll explain in another minute. But we have just a regular reference to a vec2, and it's saying initial value must be an L value. This, as I've said, is an R value. So what you'd have to do is remove the reference here and say a plus 5, and that would work just fine. I think a good way to think about this is that a reference is basically just another name for an existing variable. And because a plus 5 does not exist as a variable, you can't reference that variable because there's nothing to reference. Okay, so now let's talk about why making this const works. Well, first, actually, I'll talk about the special type for it. So you've seen this syntax here in this thing that I've called the move constructor. So we have a copy constructor here, which takes a const reference, or a reference to a const, and then under it we have the move constructor, which takes a reference, like this syntax is weird, a reference to that. It doesn't make any sense. And that's not what that means. What that is an R value reference. There's a special type just for that. So you can see here, I still have that error. If I do this, it works just fine. Now, in this case, this is admittedly a trivial example, and this doesn't really make sense because I'm pretty sure all that's going to happen is this a plus 5 value is basically just going to be converted into a new vec2 anyway, so it's not technically a reference. But the syntax is the same. So you can see here, it's yelling at me saying, hey, this is not an L value, it needs to be an L value, you can't put it in there. But now it's saying, okay, yeah, you can put that in there. So this is an R value reference, I think is what they're called. I'm not sure. There might be some other name for them. That's what I call them. But certainly the point is just to get, this is not a reference to a reference. That's not a thing. And you can't do that. You can't just, extrapolate this arbitrarily. That's not a thing. Not like you can with pointers. Now, as I showed you before, so that's an R value reference. But if I do this thing where I have a const L value reference, it also works. Oh, I need to name it. It also works. So this one, I don't think I could tell you conceptually why this works. I don't really know what it means. I especially don't know exactly what's happening under the hood. But all I know is that what this means is that we can use this syntax of const type reference to, in our method headers, to capture both R value references, which normally you would need this for, and regular old L value references, which is very nice. So we don't have to rewrite the same thing. And you can see this if I go back to our vec2 class here. And let's say I want to use this equal method. That's perfect. Very simple, and it takes a const vec2 reference. So if I want to use that, it is perfectly valid for me to say a equal a plus 5. That will not yell at me. Because even though a plus 5, as we've seen, is an R value reference, sort of a temporary value, this const reference type will capture that. If I were to make this just a regular reference, this would yell at me. Or not. Why is it not yelling at me? Oops. Okay. Maybe I don't understand this as well as I thought I did. I'm probably just doing something dumb wrong. Let's take another example here. Let's take this constructor. So we have two constructors here which perform exactly the same thing, right? They just do the operator equals. But let's add a printf in here to say this is the move constructor, and this is the copy constructor. And let's see which ones get called when we pass in various things. So I'll say, I'll create some more vec2s here. B, I'll just assign to A, and then C, I'll assign to A plus 5. Let's see what happens. Okay, so you can see here, there's only one copy, and that is B. That gives copy, which is perfect. But this is sort of a bad example, actually. I shouldn't be doing it like this. I'll get to that in a minute, because that's sort of another layer deep. Let's actually use the constructor itself here. So B still says copy, and C does not say move. Very interesting. Does anyone know why that is? Is everyone at least following a little bit, or have I completely lost people? Because this may be a bit advanced, and clearly I do not have 100% understanding either. Okay.
A little lost.
What was that?
A little lost.
A little lost,
Ooh.
yeah. So am I, honestly. I'm surprised this is not printing move. I think I figured it out, though. So we can see here when we're printing our values, they do print correctly. We've assigned A directly to B, 1 and 2. That's perfect. And we've assigned A plus 5, 6 and 7 to C, which is perfect. I think what's happening here is that our plus operator creates a new vector. Because when we have this syntax, A plus 5, this is the method that's being invoked. Let's just prove that real quick. So this should print add at the very least. Oh, I got that weird buggy window again. Okay, yeah, so we have a couple extra adds. I'll delete this up here just to clean it up. So we have one copy, which is putting B into A, and then we have this A plus 5 operator, which is creating a new vector. Now, this vector, let's see what this is actually calling. Because remember, this syntax, even though it is a bit weird, the C compiler will call a constructor, or it should call a constructor, because we've defined a constructor. So it's not calling copy, because there's only one copy being printed. It's not calling move, obviously, because move isn't being printed, so it must be calling this one. Let's just print init. So now we should have two inits, one from this initial A creation up here, yeah, and then one after this add. So this is creating a new vector. But then what's happening with that vector? Let's see if we can, so to clarify here, I am also lost. Everything I've said up to this point, up until this move constructor stuff, has been true. All the stuff about R values, L values, that has been correct and like battle tested. How const regular references will capture R value references, this sort of double thing, that's true. But I think I'm just doing something weird in this particular example with the move constructors incorrectly, and so it's not giving me the result I'm expecting. But I think it's useful to sort of debug this we have some extra time. We couldn't have gotten through the PowerPoint, and this is a pretty useful C++ topic to understand. Okay, so let's assign this actually to, I'll call this A5, to a variable. And then let's see what happens if I do this. Okay, so we have init from the A, the first one, which is good. We have add from this operation here, which is good. We have init from B, or no, I think this other init is from A5. It is. It's because I'm using equals. I keep confusing those. This should give slightly different. Okay, so we have the initial A init, A plus 5 add, A5 init, B is a copy, and then C is another copy. Interesting. Why is that? Huh. So it seems like the move constructor is not invoked in all the cases I thought it was. I'm going to temporarily disable that and just see what happens. So we can use the error output to sort of deduce what's going on here. So obviously B is not going to work because that was a copy. That one seems correct, but this one seemed a little weird to me. So what does it say? Function mathvec2. So this is the constructor taking in a const reference. Cannot be referenced. It is a deleted function. Obviously it's a deleted function because it doesn't exist, but I'm not sure why this is not calling the move constructor. Oh, I know why. That's why. There we go. I was doing something dumb. I just completely skipped a whole step. Okay. Sorry. So now if we run this, oh, I feel so stupid. Now if we run this, we should get an init from A. We should get a copy from B. We should see add printing out and then another init from this constructor down here, and then a move into C. So let's see. We have init, that's from A, copy, that's from B, add, that's from A plus 5, init, also from A plus 5, and then move into C. That's what it is. So this standard move, this is just a function. And it's used to take an R value reference. So one of these, double ands, and keep it as that type of value, because otherwise it seems to decay into some other type of value. So let's just verify our output once again. Init copy add init move. Okay, now let's remove this standard move function here. Init copy add init. So you can see what's happened here, I believe, is a compiler optimization, where even though we've said, okay, we have this new vec2 called C, and I want to call this constructor with some vector, one of these two, it doesn't really matter, that is A plus 5. Because we know the plus operator returns a vector, right? But if we look at the output, we have init from A, which is good, copy from B, which is good, add from here, init from here, those are both good. But then there's no constructor call at all for C. There's not another init, obviously. That wouldn't make any sense because that takes two values. But there's not a copy or move either. So I'm glad we did this exercise because we actually get to see a little bit of what's happening under the hood. What the compiler's doing here is it's saying, okay, So I have this sort of temporary value of a plus 5, which is returned by this operator, right? It's stored somewhere. It's not yet a variable, but the data exists somewhere in RAM. And all I'm going to do is I can see that you're trying to create a new vector with this value. I'm not even going to call the constructor. I don't need to do that. The compiler has outsmarted us here, and it said, okay, I'm just going to set this memory into C automatically. I don't even need a constructor. I'm just going to move it for you. So that's what's happening here. That's what was confusing me. But if we do this the, in quotes, proper way, to actually call this move constructor with standard move, you can see that we do get this move output running. And this now has some little squiggly underline. You may see this sometimes. Red squiggly underline means overload, or sorry, not overload, like error, incorrect syntax or something, or compiler error usually. Green is usually, I guess, a warning, or maybe just something that the compiler has like thinks might be an error, but it's not gonna it's not gonna yell at you about it. So in this case, it says like this kind of function may not throw, declare it no except. Exceptions are not something we're going to do at all. They do exist in C++. I think, literally never used them. They seem to be a much bigger thing in Java, much more common. But if we just go ahead and throw that on there and then rebuild, this should stop yelling at us here. Yeah. Sometimes you have to reload the file, unfortunately. And we might see that too when we're like creating new files. It like won't highlight your syntax at all at first, which is very frustrating. But anyways, yeah. So I think what I'll do is I'm going to look a bit more into standard move because admittedly and very clearly I don't understand it fully. But I also want you guys to do the same because this was like a very interesting sort of dive into what C++ does. And if you're new to C++, this could I could see how this like just immediately becomes overwhelming because there's a lot of stuff that you're not familiar with. Even if you're coming from like another compiled language like Java or C#, you never really see the effects of any compiler optimization. But here you can see directly, like the C++ compiler said, I'm smarter than you. I'm not going to call this constructor. There's no need. I'm just going to move the memory myself. And we had to explicitly tell it, no, I want you to take this, move it into here, and do the whole process. So compiler optimization is a very advanced topic. I'm not even claiming to know like almost anything about it. I just know that it exists, and I can sometimes detect it. But there is one general rule when it comes to this stuff, which is never try to outsmart the compiler. Because it will probably lead to less efficient code than if you just let the compiler do its thing for you. And one thing that I was sort of prepared to talk about if anyone was a bit more experienced in C++, a lot of these methods are like very simple, right? They're just like 2 or 3 lines, especially these one-line ones. I was prepared for someone to say, hey, why don't you mark these as inline? And this is sort of a misnomer. This is a keyword that seems as though it means, okay, I want the compiler to inline this method into my code. Don't even make a function call. Just take whatever's in here, copy it directly where I've called it. But that's not at all the case. And that's another example of like trying to outsmart the compiler. Usually just doesn't do anything, but also could potentially have negative performance impact. So I'm going to give you these 2 articles, and this is such a great resource. CPP reference, like you should have this bookmarked. It's so great. It's very detailed explanation, obviously. Some of this is just like so verbose you don't even need to know it, but the code examples really, really make it so helpful. And they have this for everything, like all of the standard classes we'll be using, vector, string, file streams, stuff like that. So if you ever have any questions about anything, first come here. And then, you know, if you still can't figure it out, if it's like a weird special case, then feel free to ask me. But yeah, so I'm going to give you this article, standard move, and then I'll also Google CPP inline, going to the same CPP reference thing. And I actually read this the other day and learned some very interesting things. So this standard move one, like, you should read this first just because it's directly related to the big jumbled mess of an example that I gave today. And that should help you figure it out. I recommend tinkering with the code yourself and you know, doing these sort of basic printfs to see what is actually being called in what order, and what happens when you add standard moves in there, and what type of references get captured, that type of stuff. It's not extremely important, and again, I don't want the focus of this workshop series to be C++. It's sort of just like an auxiliary thing that you'll get some more experience with. But especially if you're new, I think references in general can be very confusing, and just tinkering with them like this, referring to, you know, the official documentation on this stuff, is very helpful. So yeah, sorry that was like a 30-minute long ramble, but I didn't want to jump into our graphics thing and just like get halfway through it and have to start over anyways next week. So we did a bit of a weird example there. Hopefully you got something out of it. If it was just completely, totally confusing, I'm sorry. If you want me to explain it again at the top of next week, I can. I'll give a more refined example. But yeah, I would highly recommend, if you see anything that's just weird, weird syntax especially, there's a lot of that in C++. Like, you know, we just throw const around like it's, you know, like it grows on trees. It's very helpful to go here, go to these pages, see, you know, the what these different types of syntax all mean. So yeah, I'm going to stop rambling. We got through our math library. As I've said, next time we're starting on graphics. We should definitely get into some basic graphics programming next time, some basic setup stuff, at least getting a window set up. But first we're going to go through a presentation about, like, we're starting with, like, what is a pixel? You know, how does that work? How do pixels get to your screen? What's the job of OpenGL? How do we interact with it? All of that kind of stuff. So just probably a 30 to 45 minute crash course in the fundamentals of graphics programming. So hopefully you're excited for that. I definitely am. I think this is where game engine programming, like, really starts to get interesting, because up to now it's just not very interesting. It's just like utility things that we'll eventually use at some point. But starting next time, we'll be writing code that we will immediately be able to see the results of and immediately be using, and it's very cool. So hopefully you're excited for that. And I will see you, what's that? Saturday at 4.